This is Josh White with JW Math Tutoring. In today's video, I'm going to go through some more advanced use cases of regression, including solving advanced percentage problems, finding the value of a constant for a system of equations that have no solution, and finding the maximum or minimum value of a constant for a quadratic equation to have no real solutions. So let's go ahead and get right to it.
But life is a dream that calculus could never predict.
I am back to share some more tips and tricks to use in Desmos to help you ace the digital SAT math section. So in this video, I'm going to go through basically 4 new operations, basically ways that you can solve problems in Desmos. Some of the problems are familiar types of problems you've seen before. It's just basically a new method or an alternate method you can use to solve them. I'm also going to first go over, though, an alternate method you can use to solve formulas. And this method that I'm going to talk about first will apply to either of the two previous types of problems that I've gone over in a previous video as part of this guide. All right, so just before I start going through those, a couple things. First of all, you can find a link to the guide itself, the instructions or the actual operations, what you see on the left side of the screen right now, in a PDF file, in the pinned comment, or also in the description of the video. Second, the problems that I'm going to work through, you can find a link to all of those as well. Currently up to 65 total problems. Again, a link in the description or in the pinned comment on the video. Now, if you've already done all basically the first 58 problems and watched my previous videos, there will also be a link to just the new problems, basically 59 through 65, that I'm going to demonstrate in this video. Just be aware, the first 2 problems, I'm going to show alternate methods to solve the 2 formula problems, which are in like the 30s, that I've already done previously. So those will not be in the, the new separate problem thing that's only for like the 4 new operations that are on the last page. They're just in the main guide, basically. I think it's 36 and 37 we're going to take a look at. All right, so with all that being said, I got my Desmos window up here, College Board version. First thing I want to talk about is the following. Solving a formula for a specific letter. So there are 2 different types of problems that you could come across where you have to solve a formula for a specific letter. So there's the one type of problem where you have one letter equal to everything, and then there's a second type where you have basically multiple letters on both sides. The approach to each of these is slightly different, just because one of them has one letter equal to everything else versus the second one. However, this alternate approach I'm going to go through will work with both types of these problems. So essentially what you're going to do is you're going to take the formula you're given, but you're going to type it in as a regression statement. So you're going to type the exact equation that you're given, but just use a tilde instead of an equal sign. It's going to automatically pick or fill in values for all the letters in the formula. Then you're just going to type the answer choices and see which one matches the value for the letter that you're supposed to solve for, because the value for that letter is going to be in the regression statement. So one thing just keep in mind is that you can still pick values for individual letters if you want to. You can still add a slider for them. Just for some reason, there's certain conditions that you have to meet in the problem. A specific letter has to be greater than something or less than something. Or if you have 2 answer choices that give you the same result and you need to redo it, then you can go and change one of the values of one of the letters from the regression statement. Okay. So let's go ahead then and let's look at, again, these are previous examples that were already in the guide, that were basically demonstrated in a previous video, but I'm going to show you how to go through them today. So in the first one, right here, number 36, where we have one letter alone equal to everything else. All right, so I'm just going to do the regression statement. Okay, so notice it picks a value for p and it picks a value for n already. Now, in the conditions of the problem, it says n is not equal to 0. Okay, good. N is 1. And then it also says p is greater than 8. It's 23. Okay, so those things both work so far. All right, now, all I'm going to do is just type the answer choices. And I'm going to see which one has the same value for n that is in the regression statement. So A matches, B does not match, C does not match, and let's check. Okay, so notice here D gives us the same value that A does. So this is a case where, first of all, let's get rid of these. We don't need B and C. This is a case where now I would pick a different number for n. So I would say let n equal 2. So now, notice it gave me different values for p. However, that new value for, excuse me, different value, one value, that new value for p is automatically fed into my answers. And now you can look at the answers and you can clearly see D is the only one that still has the same value. In other words, D is saying that n is equal to 2, and n equal 2 is the value I chose. Therefore, D is the correct answer, A is not the correct answer. Okay, so that's just an alternate method of how you could solve a formula. And in this example, when it's one letter alone by itself, everything else on the other side. All right, let's take a look at the one below it, 37 now. So here we can do the same thing. We can just type in the entire equation, but just change it to a regression statement. Notice it picked values for Q and P and R. So now if we want to solve for Q, we can just go through and type in the various answer choices and see which ones match. All right, so we've got A looks pretty close to matching. I mean, the value in the regression statement might be the 7 at the end because of rounding. B is obviously incorrect. Let's see here. This one is undefined. Okay, so that's not going to work. And D is obviously incorrect as well. So for this one, correct answer is going to be letter A. And again, all we had to do is just type the original formula as in a regression statement. It automatically assigns values for Q, P, or R. Then just type all the answer choices and see which one gives you the same value for Q that the regression does. Okay, and obviously A is the only one that basically is the same. It's not identical because up here, I'm assuming this parameter is being rounded. That's why it has a bunch of 6's and then a 7, whereas this one goes out to more decimal places. But it's clearly the one that is closest enough to Q. All right, so now let's take a look at some of the new operations in the guide. So these are all going to be on the last page, basically page number 8 that we're up to now. Sorry, not page 8. Yes, page 8 right here. Okay, so first thing we want to look at, using sliders to solve a single equation with a constant non-graphing method. This is actually an alternate method of something that I talked about previously. So just to show you, if we go back to, here it is, page number 5, right here below all the different types of regressions, use sliders to solve a single equation with a constant. So when I first went over this method in one of the previous videos, I'll put the thumbnail up on the screen here, just to remind you which one. Basically what I had to do is graph the left side and the right side of the equation and then find the intersection points to get the solutions. But you actually don't have to do that. And this method using regression is going to be a little quicker and easier because it'll just give you the value right away. You don't have to search for anything on the graph. All right, so essentially what we're going to do is we're going to take the equation that you're given. You're going to type in exact regression statement, and change all the x's to x1 sub 1s and replace the equals with a tilde. Add a slider for the constant, or if there's multiple constants, add a slider for both of them. And then it's going to give you an answer for x1. Then you're going to type in all the answer choices and see which one has the same value as the solution that x1 it's found in the regression statement. The reason this is better is, as I mentioned, it can be easier to just compare the numerical values than trying to find the actual intersection points on the graph. And second, a thing you may need to be aware of, you might have to put in condition, to tell it to grab the positive or negative solution based on what the answer choices are returning. So whether the answer choices are all positive values or all negative values. All right. So with that being said, let's go ahead and look at this problem. So this is going to be, basically in the packet now, starting the top of page 18, problem number 59. So here's my equation. K is a constant. Which of these following expressions is a solution to this equation? All right. So all we need to do is type in again this whole equation, but I'm going to change the x's to x1s. Quantity squared, replace the equal sign with a tilde. Go down, okay, x1 squared plus 4. Okay, next, set a value for the slider. Notice it automatically picks one here, but I'm just going to choose, whatever. Maybe I'll pick 20. Okay, so now I'm going to go through the answer choices. I'm going to type each of the answer choices. And I'm looking for the one, so A is obviously wrong, B is obviously wrong. I'm looking for the one that matches the x1 value in the regression statement. Okay, so far it looks like C is also wrong. Let's check D. Okay, so for this one, notice the value we have up here is 20.00625. Okay, down here, okay, A and B are obviously wrong. They're way too big. The answers are going to have a square root in it. So let's just get rid of those, clear things up. Now, in comparing these two, it looks like it's D, but notice D is negative, but this is positive. So that's because there are actually two answers to this. There's a positive and a negative, because if you solve this out by hand, you have to take the square root. So what I'm going to do is just put in a condition there. Basically make x1 less than or equal to 0. That will give me the negative solution. And now what I have for x1 here matches what I have typed out for answer choice D. Again, it's 0.625 here because of rounding, whereas down here it has more decimal places it can display. But D is the correct answer for this problem. All right, so now let's jump back to the guide and let's talk about the next type of problem that we're going to look at. So this is solving advanced percentage problems using regression. There's actually two different ways you can do these. The first way is just basically the way that I've demonstrated in some of these problems that have come up in the Blue Book test, which is where you type an equation for the various pieces of information that you're given. Except the last one's actually going to be a regression statement, and that's going to be the one that's going to solve for the constant. So if you use this method, you can use the percentage sign in all your equations, whatever, p percent of, whatever, 222% of. The problem is, though, and we'll look at this as an example, if you have two equations and they both start with the same letter, so like A equals blah, 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 and then A equals blah, 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 it's not going to work, okay? They have to be set, if you're going to take this method, they have to be set up differently. So in other words, you will need to rewrite one of them so that if one equation is A equals everything else on the right, the other one can't be A equals. It could be B equals, it could be C equals, whatever equals. It can't just be A equals, otherwise it doesn't work out properly. That's the first method, so I'm going to go through and show you how to do that. and then we'll take a look at the second method after that. So now going to the worksheet, we're looking at question number 60 here. So we have three constants, A, B, and C. Okay, so A is 235% of B. Okay, B is equal sign 3.4% of C. C tilde P% of A. Okay, so notice I typed in basically the first thing as an equation. I typed in the second thing as an equation. Then I type in the third thing as a regression statement. It solves this for P, and because I typed, P%, this is the actual number I want. What's the value of P over 1,000? P divided by 1,000. Right there. So your correct answers for this would be 1.251 or 1.252. And this would not be an acceptable answer because it doesn't, you can't reduce it or simplify it any, further. There's too many characters to type in. You have 1,000, which is 4, then the division sign is 5, and so you couldn't fit the 799 in. So you'd have to enter this example, just the way that this is worded for this specific problem as one of the decimal values. Okay, so this is how you could do number 60 using the first method. Let's take a look now at number 61. So A equals 626% of B. A is 0.72% of C. C is P% of B. Okay. What is P rounded to the nearest whole number? All right. So if you notice what's happening here, it's just like choosing B as 1 and C is 0.01, P is, whatever, like P is just 1. But this is not correct. This is not the correct value for this problem. Again, this is the issue I spoke about earlier where if you have the same, both equations have the same letter equal to a bunch of stuff on the other side, it will not work. So what you have to do is you have to rearrange one of them. So that means, unfortunately, you're going to have to basically take one of the percentages and convert it to a decimal. So for example, get rid of this and just change it to 6.26 times B, which is the decimal equivalent of 626%. All right, so notice just doing that in of itself, that didn't change anything, right? Everything else stayed the same. So now what you're going to have to do, though, is you're going to have to say, get rid of this, and actually, there. This is what we want. So now, notice when I type everything in here correctly, it gives me the correct answer down here in the regression statement. All right, so now we have our answer, and since we want to round this to the nearest whole number, because that's what the instructions in the problem are, we can just go ahead and we would just put 86944, and that would be our correct answer. Also for 60, just since I didn't write it down at the time, reminder, either 1.251 or 1.252 would be accepted, and for 59 it was letter D. Now, let's go over the second method, which is basically solving these advanced percentage problems using systems of equations. So I'm going to jump back to the guide here, but first let me just erase the answers, only because they'll be basically over top of it. All right, so solving advanced percentage problems using regression. This is the second method. Basically, all you're going to do is you're going to take these equations, that I had set up originally, technically two equations and like one regression statement. You're going to put them into a system of equations as part and basically solve that using a regression statement. You can still use the percentage signs in the system of equations. And the one thing that makes this a better approach is that you don't need to rewrite or rearrange any of the equations, okay, in order to do this. So it's basically just going to be like in the first set of brackets, the left side of the first equation, comma, second equation, comma, third equation. and then the tilde, and then in the brackets on the right, it's going to just be the right side of each of the three equations. All right, so let's go back to the problems now. So let's look at 60 again. So remember the first equation was, and I'm just going to set two things up here and fill in left and right parts and jump back and forth. First equation was A was equal to 235% of B. Okay, so I'll fill that in first. Then we had B, put a comma after it, was 3.4% of C. Also, let me just stretch this out so you can see the whole thing. And then the last thing was C was P% of A. All right, so notice here, it found values for A, B, and C, and more importantly, it found a value for P. So what is the value of P over 1,000? There it is, exact same answer that we got previously. You know, you can either put it in as 1.251 or 1.252. So notice, I would say this is a little bit cleaner, you know, a little bit quicker and easier than writing them out on separate lines. And you also, this one we didn't have to rearrange any, but we did in the next one we're going to take a look at. All right, so now let's go ahead and look at 61. So let's clear this all out. Okay, so again, I'm going to set these two brackets up. We know that A was equal to 626% of B. Then we also know that A was equal to 0.72% of C. And then lastly, we know that C is P% of B. So again, notice here it shows values for A, B, and C. Those aren't really what's important. What's important is the value for P. That is what we are asked to find. And in this case, again, since it's rounded to the nearest whole number, the answer that you would enter is just going to be 86944. So that's how you could solve this advanced percentage problem by typing everything into one regression statement. Basically, it's a system of equations. You know, you're putting in three different equations, and it finds the value of P without any issues or problems. The next Desmos operation that I'd like to go over is finding the value of a constant or constants for a system of equations that have no solution. So this is an alternate method that you can use because I already covered how to do this previously in one of the earlier videos for my Ultimate Desmos guide. I'll put that up, the thumbnail up on the screen for the one that it's featured in. But this is just another method. So this was actually suggested by a commenter on my YouTube channel. I don't know how it's pronounced, but Hygen6. Name will appear on the screen. But basically what we're going to do is you have your two equations, your system of linear equations. You need to make sure that the x and y terms in both equations are on the same side. So think of both of them as being in standard form. Now, technically they might not be what's considered standard form because standard form you're not supposed to have fractional coefficients. So that's why I don't say standard form here, but just move all the x and y terms over to the same side, either both on the left or both on the right, and they can be different for the two equations. You know, one of them can have them on the left, the other can have them on the right. That's fine. And then you're going to solve a system of equations using regression, but you're going to set them both equal to 0. And the regression is going to return the value of the constant or constants. Now, one thing just to mention before we begin, if there are two constants that you're solving for, technically the only thing that you can find definitively is the ratio of the constants. There could be multiple correct values for the constants themselves, like for P and Q or P and R or A and B, whatever. Because in a no solution case, essentially the scale factor, the multiplier between the x and the y terms has to be the same from one equation to the other, but for the number term it doesn't. So It's different than an infinite solution case where all three sets of values have to have the same like multiplier or the same scale factor. So the x and y terms, the coefficients for those, are not constrained like they are in an infinite solution case. So just keep that in mind. All right, so with that being said, let's go ahead and get to the problems. All right, so first one I want to look at here is number 62 at the top of the page. This one has one constant, and what we need to do first is notice that there's an x term on the right side that we're going to need to move over to the left. So we would have to add 2/3 x to both sides before we could go ahead and set this up. Now on the right side, of course, this would cancel out and we're left with just a number. That's what we want. On the left side, we now have everything we can type in. So we've got 2/3 x, and again we have to use x1 and y1 because we're solving a regression. Okay, so that's the entire left side of the top equation. Bottom equation, we can just type it in as is because the x and y terms are separated. And now we just do a regression, set them each equal to 0, and there's our answer, 26/25, or in fractional form, 105/4. So again, 26.25, or as a fraction, 105/4. Now, let's just confirm visually that this value appears to be correct. So I'm going to take the original equation and just graph it out. Of course, for this, I'm just using x and y, not x1 and y1. So there's the top one. Here is the bottom one. And notice here, let's just slide this back. Yes, these two lines do appear to be parallel. You know, I mean, you can scroll to the left, scroll to the right, but it does not look like they are going to intersect at any point. You know, the distance between them appears to remain constant. So that's the basic approach. Now let's look at one below at 63 that has two constants. All right, so again here, notice there is a y term on the right side in the top equation, so we're going to have to add that over to the left. And again, we don't need to combine the terms. Just add that in there. Okay, so these all drop out. Now we're ready to go ahead and enter in the system of equations. So the top 2/3 y1 plus 3p/7 x1 plus 2/3 y1. That's all we want. Left side with the x and y terms. And then the bottom one, 3x1 plus 3r/2 y1. That's it. That's already set up. X and y terms on the same side. And then 0, 0. All right, so now we have our values for p and r. As I mentioned earlier, there technically are multiple values that could exist here for p and for r. The ratio between them, basically the ratio of the slopes really, is the only thing that's going to be constant. But the actual values themselves, there's an infinite number of possibilities. So what is p over r? Well, it looks like it's 1.5 repeating, or as a fraction, 14/9. So the way you would write this, if you had this question on an official exam, you know, you could truncate the decimal, which would be 1.555. You could also round the decimal, 1.556, or you could also, again, do the fractional form, which is 14/9. Now let's just double check real quick here. So I'm going to type in the original equation without any changes. There's 1. 3r/2y equals 3/4. Okay, and there is the second equation graphed out. Again, we can zoom out. This one we can zoom out a little bit more. And you can see, yes, these two lines do appear to be parallel. It does appear that they are never intersecting or never going to cross. So Again, this is just an alternate method for how you could find the value of a constant or constants if you have a system of equations where you're told that they will be set up to have no solution. All right, so let's take a look now at the last new operation to cover in this video. Basically finding the max or min value for a constant in a quadratic equation to have no real solutions, and this is using derivatives. So this is what I call the derivative method. This is not the same as say a slider method, which I had demonstrated in an earlier problem. Just moving a slider for b to finding out how high or how low it goes to where there are no x-intercepts. This one I should mention also another comment from a person on my YouTube channel. Again, I apologize, I don't remember the exact username. I will post it on the screen here so you'll see it in the video. Okay, couple things to mention. Basically, what you're going to have to do is you're going to have to type the quadratic function, in as a function, just f of x equals, you can say, and then also do a g of x equals 0 for the second function. Then you're going to type the exact same thing that I went over in a previous video, which is basically used to find the intersection point of two functions. This regression statement here. Notice it has x1 in the statement, the regression statement. It's got f of x, f prime of x, which is the derivative, g of x, and g prime of x. So a couple things. First of all, the quadratic must have all the terms on the same side equal to 0. If it's not given in that form, then you have to move terms over to the other side. A couple other things. The value could be the maximum or minimum depending on which constant you are solving for, say like b versus c. Basically with b, I'm talking about the standard form of ax squared plus bx plus c. So for b, the value could be a minimum or could be a maximum. All right, basically, typically it's going to have like a positive value as the max and a negative value as the minimum. However, for C, there's usually only going to be one value, and it's either going to be a maximum or minimum. There's not going to be two different answers. And the way you can check for this, specifically if you have a case where you're trying to find the value of b, is just to put in a condition in the regression statement. Set it greater than 0 or less than 0, depending on whether you want the maximum or minimum value. All right, so let's go take a look at some example problems now. Okay, so next up, question number 64. Here we have a quadratic equation. All right, and b is an integer constant. There's no real solutions. What's the largest possible value? So first thing, go ahead, type in the function itself. Don't worry about adding a slider. I'm not going to deal with that. Then type in the second function of, say, g of x equals 0. Now we do the regression statement, f of x1, comma, f prime of x1, tilde, g of x1, comma, g prime of x1. Okay, let me slide over so you see the whole thing. So notice here, it gives me this negative value. The value returned for b is negative 50.5, but that value is technically intersecting the x-axis. It's basically right on the x-axis. The vertex is right on the x-axis, right here. So, two things. First, this is not the largest possible value of b. This is actually the minimum or smallest possible value of b. Because if I now put in the constraint to make b positive, notice it gives me the same number, but just in a positive form. And notice the graph technically flipped to the other side here. So the largest possible value for b is this 50.596444. Okay, but that's not an integer. So the real largest possible value is going to be 50. And the reason that you can confirm or check that it's 50 is because once I step down from 50.59644 to 50, notice it jumps up and there are no real solutions. Whereas if I instead went to 51, notice it moved it down, the vertex down, and now there are two real solutions. So for it to have no real solutions, the largest integer value is going to be 50. So that's the correct answer to this problem. Also notice the if the question asked for the smallest possible value, it would just be negative 50. And so typically when you're solving for b, it's always going to work out in that case where it's like the largest possible value is some positive number and the smallest possible value would be some negative number, right? And then and basically between those, when b is between all of those numbers, those two values, it's when there's no real solutions, and then on the outside, it's when there's going to be two real solutions. Okay, at least for these cases where all the a and c values are all positive. All right, so now let's go ahead and take a look at one that's slightly different, which is question number 65. And so in this one, now you're solving for c. So here I have 5. Change this to c. Okay, g of x equals 0. Get rid of this. That doesn't help us. All right, so we can also get rid of this. All right, and just to save time from retyping the statement, we can see here that we get an answer for c. Okay, it's 36.45. However, this one, notice it's saying what is the smallest possible value of c. So, okay, it obviously can't be 36.45. That's not an integer. So the question is it 36 or is it 37? Well, let's just double check here. If I put in 36, do I have no real solutions? No. Okay, so then it has to be 37. So the smallest you can make c is going to be 37, and that's going to be your answer. And so here's the difference between basically b and c, solving for them in this type of problem. So when you're solving for c, okay, we have this slider here, right? And let's just say I bump it up from like whatever, negative 200 to 200. I'll set the step value at 1. All right. So what happens is as I make the c value smaller and smaller, and you'll have to zoom out and see this. Notice all it's doing is it's moving it's shifting the parabola, quadratic function essentially, straight down. Okay? So basically, there's not going to be a point or like a range like there is in number 64 where you're solving for b. And what I mean by that is basically, once you get up here to 37, that's as low as you can go for c in this case to have no real solutions. You keep going higher and higher and higher. It's just shifting up, 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 up. Because c, again, is basically your y-intercept value. The value when you plug in 0 for x, first two terms cancel out, and you just get c. So when you're solving for the constant, the c, basically what you call the c constant in this type of problem, there's only going to be one specific answer, and it's either going to be largest or smallest depending on the direction of opening. Like if this opens up, so therefore it's going to be smallest possible value of c. If I took this and I made it negative and it flipped, basically if you notice what happens, let's zoom in here. Yeah, basically then it would be the opposite. Negative 37 would be the largest possible value of c. Because if you go above that, if you make it larger, notice now you do not have any real solutions anymore. You have two real solutions or two x-intercepts. So that's one thing. That's basically the difference between 64 and 65. Or excuse me, yeah, 64 and 65. Finding the value for b versus finding the value for c. And just to show you one last thing again to explain this, if I type in 64 again, so here's the problem, and here's it's like notice here at b at negative 51. So let's go from negative 51 to 60, and let's set the step at 1. See, notice when I'm less than negative 50, right, there are two real solutions. You can see right here, there's two x-intercepts. But then, as soon as I get above that, notice, see, it's like way up here. There are no real solutions. And it keeps going, and then eventually, see, notice how it went up, and then it comes back down again. And then eventually, it crosses again. You know what I mean? It reaches that upper boundary of 50, and then crosses that, and then now at 51, we're back to two real solutions. So that's just a visual demonstration of how the problems are slightly different when you're looking for, a value of B versus a value of C. All right, so I hope you enjoyed this most recent addition to my ultimate Desmos guide for digital SAT math. Have any questions or comments or feedback, please do leave them in the video below. Also, if you haven't done so already, do check out the other parts of the guide, of course, basically core skills, intermediate skills, advanced skills, and then a bunch of separate videos on regression as well. Also, if you haven't done so, check out some of my Desmos hacks videos on select problems from the Blue Book practice tests and how to solve them using Desmos. Check out my 25 hardest SAT math problems and how to solve them using Desmos. And lastly, of course, check out the official test problem playlist, which basically has anywhere from 3 to 4 worksheets for basically every month that there's an official SAT exam. The self-reported problems, but I've gathered them, I've worked them out, anywhere from 9 to 11 problems per worksheet with full video solutions. Otherwise, good luck as you prepare for the digital SAT math test.